If we consider that same graph from the previous pages again, with the upswing, the downswing, the upswing, the downswing, we can actually make some correlations between this graph and the graph of its derivative. And the graph of the derivative is simply constructed by, at each point, calculating the slope and then translating that into a value down on the next graph. So every time we look at a slope value here, it becomes, let's call it a y value here, because it's on the vertical axes. With that idea in mind, it becomes pretty straightforward both to construct the derivative graph, but even easier to identify key features that tie the original graph with the derivative graph. Now, at first glance, they have just similar shapes, but that's actually a bit deceptive. It depends a lot on the original graph. What we can definitely say they have in common are that when the original function reaches a peak or a point of slope 0, that'll translate immediately in the graph of the derivative to a value of 0. So whenever you're trying to map from the original function down to a graph of the derivative, imagine slopes being converted to values. All right. Other landmarks would then be this point D here, where the tangent line slope is 0. We get a 0 value on this graph, and the same at F. What happens in between those points? Those are the landmarks that are most easily identified visually. 0 slopes are really easy to see. What happens in between, say, B and F? Or sorry, B and D rather. Well, the slope is always negative. The slope is always negative in that range. And so what we have on our graph of the derivative is values that are negative. Okay, everywhere, if we calculate the slope, we'd have a value of like -1, -2, -3. That would translate to values down here of literally -1, -2, and -3. The most distinctive point on this graph anyway is this lowest value here. And it's worth making that association in reverse. So this is the largest negative value. And with the relationship between these two graphs, that means that C translates into the largest negative slope. So that's the correlation between all these things, between both these graphs. The same kind of pattern applies on the positive branches as well. When we have an increasing function, we'll do that in a different color, shall we? Let's do that in blue. When we have an increasing interval, the values are positive. So positive slopes lead to positive values. And once we go to the far side, we go back to negative slopes on the original graph, negative values on the other graph. Just to remind ourselves what the notation might look like here, if this graph is given by f of x, this could be called f prime of x or df dx. And this is just like giving a formula for the derivative, except it's giving it in graphical form. We would start with this graph here and then ask at each point, what is the value of the slope? And then plot the value of the slope, not slopes, or we don't worry about slopes in this graph. We take a picture on this graph, find the slope of a tangent line. What is that numeric value of the slope? 1, 2, 2.7, and translate it into a y value on this graph below. All right, hopefully that made some kind of sense. Here's a chance to practice. Consider this graph here, which decreases, then goes through 0 here, and then increases and slows down. I'm going to ask you to think about for a second which graph on the next page is the derivative of this graph here. There's the graph again. I'd like you to take a look at those 4 graphs and, using the same kind of logic we used in the previous example, identify which one is the derivative of this function here. I'll give you 5 seconds. You can pause the playback, and then we'll discuss. Okay. again, the most distinctive feature about slopes of a graph are the points where the slope is equal to 0. So if this is our original graph, whatever graph we pick for the derivative has to have the corresponding, not slope 0, but it has to have a value of 0. And all three of these graphs here share that. This one up here does not. So this graph here has a value of 2. What we need to see at x equals 0, what we need to see on this graph would be a slope of 2, and we don't see that. So that rules out the graph A. Okay, that still leaves us with 3 choices though. The next thing we looked at were the signs of the slopes. In this interval here, the slopes are negative. So whenever x is less than 0 here, we have negative slopes, and that means we should have negative values on our derivative graph. So again, just to sketch this out or label these, this would be f of x, and one of these is f prime of x. So negative slopes here, -2, -1, and so on, would translate to negative values of -2 and -1 as values on this graph. So this graph might work, and also this one, and this one would not. The values here are all positive. If we had this as our derivative, this would mean at this location here, the slope must be 2. Here the location is more like -2. All right. Last but not least, we can look at the branch on the right-hand side here. And these slopes are all positive. And as with the negative slopes, that translates on the derivative graph to positive values. And if we look at this branch here, these values, don't look at the slopes, just say this is a number, the point, the point, the point. These values are all negative, and so it cannot be this graph. So at the end of the day, we end up with graph C. And we should be able to take a holistic view here. We've got steep negative slopes approaching a 0 slope. We have large negative values approaching a 0 value. Then we've got, from the 0 value, we've got positive slopes that are initially quite positive, and they actually go back down almost flat here. If we look at the slope, it's close to horizontal. So the slopes approach 0 again, just like they did over here. So the values here start at 0, go positive, and then approach 0 as well. So this graph here, letter C, would represent the derivative of the graph of f of x.